In this video, we're going to be talking about meters. Now, for most HVAC technicians, the meter is your most often used tool. At least it should be. The meter should be your first tool out of your tool bag, and it should be the last tool you put away. It's important to read the manual that came with your meter to understand all its functions. Now, the reason that we want it to be the first tool out is in order to safely work on equipment, you have to know whether or not you have voltage. Should also be the last tool you put away because you should be checking all your work once you're complete. Most meters also have some temperature gauges on it, temp sensors, so you're going to use it all the way through. There are two basic types of meters on the market. First, the analog meter, which has been the workhorse for years. They were the first meters on the market. They're extremely sensitive and don't stand up well to being tossed around trucks. They're still used today when technicians are looking for extremely accurate measurements. This is an example of an analog meter. Okay, it has a needle that moves around, stays at zero, spring driven, some connection points for leads. Digital meters have almost completely replaced the analog ones in the industry. Digital meters stand up much better to being dropped, tossed around a truck in a wide range of temperatures. Digital meters are also accurate and also auto range. By auto ranging, you do not have to select the range that your meter is going to be working with. For example, like 1 to 10 volts, 10 to 100 volts, 100 volts to 1000 volts. That's all automatically done. The one note I want to make on digital meters, it's extremely important the batteries are good. If the batteries start wearing out on a digital meter, the meter will no longer work properly. This is an example of a digital meter. This is an older style, but again, it has a digital readout. So there are several basic electrical rules you really need to understand prior to understanding what a meter is telling you. Most of these rules are based on voltage and resistance. First of all, just a quick review from my video 3. You'll sometimes hear technicians talk about things in series with something else. In series just means in the same line as. We'll talk more about series circuits in the next section. This is an example of a series circuit. The red ball is in series with, the yellow and the two blue balls. Okay, there should have been a green ball in here someplace, but it vanished. So the red ball is in series with the first blue ball and then the next blue ball. Parallel. You'll also hear technicians speak about things in parallel. Parallel means next to. We'll talk more about parallel circuits in the next section. This is an example of a parallel circuit. The red, the dark blue, and the green ball are all in parallel with each other. But in this case, again, just be careful. Some of the colors have changed. The yellow, the dark blue, and the light blue are in parallel with each other. Open circuits are circuits that do not have a complete path for electricity to flow. Open circuits require a source, switch, path, and a load. If any of these components has a break or an open in it, the current cannot complete its circuit. So again, very important to remember, a circuit requires a source, a switch, a path, and a load. If any of these components has a break or open in it, the current cannot complete its circuit. So this is an open circuit. The open is at the switch 1 or SW1. That switch is not closed. There is a gap right here where the current cannot flow. When you measure voltage across an open circuit, you will always get a reading of source. When you measure resistance across an open circuit, you'll always get a reading of infinite, or OL, on most digital meters. All that means is the circuit is open. Closed or complete circuit. A closed or complete circuit is one that has a complete path. It has a source, a switch, and a load. The load is operational in a complete circuit. The switch is closed in a complete circuit. Same circuit as I had a couple slides ago, but SW1, the switch is closed. So you can see that from line through the load to neutral, there is a complete circuit. When measuring voltage across a switch in a complete circuit, you will always get 0 volts because voltage across a closed switch is always 0. When measuring voltage across a complete circuit, you will get source. When measuring, and I'm going to add one more in here because we have voltage across loads. Voltage across a load is identical if the load is working or if the load is bad. If you have all the switches closed and measure voltage across the load, the circuit is good. If the load is not working, then you have a bad load. If the load is working, then the voltage you read is the voltage the load is using. Current or amperage you measure will be 0 in an open circuit because there's no movement of the electrons. In a closed circuit, the amperage you measure may change based on where you take your readings. Because remember, in a parallel circuit, the amperages will vary between branches. Okay? In a series circuit, the amperage should be the same all the way through the circuit. Most meters will measure voltage, current, resistance, capacitance, frequency, and temperature. Voltage will be one of the most frequent measurements you make. To measure voltage, turn your meter on, set it volts or V, make sure you have AC or DC properly, okay, and make sure your leads are plugged into the correct place on the meter. Put the leads in parallel or next to the point in the circuit you're trying to measure. Your meter with voltage will always be in parallel with the circuit you're trying to measure. Hold the lead steady without touching any of the metal to your fingers or each other. Watch the display until the meter stabilizes on a number. That is your voltage reading. So voltage across an open switch is always source. Voltage across a closed switch is always 0. Voltage across a non-powered load is going to be 0. There's no path for electricity to flow to the load. Voltage across a powered load is always source. Voltage across an open powered load, in other words, broken, there's a winding broken or a filament broken, light bulbs burnt out, it's always going to be source. Again, because there's an open in that bulb or load. Voltage across a full circuit should always be source. If you don't get source across a full circuit, go find out why. Now, resistance is a little bit different than the others. Okay, to measure resistance, you have to disconnect the circuit from a source. With resistance measurements, there cannot be any power on that circuit. Decide what component or portion of the circuit you would like to measure. You have to disconnect wires to or remove that part. For resistance, we want to isolate any components. Set your meter to ohms and touch one lead directly to the other. We want to verify our meter's good to start with. Okay, that will show a reading of 0 on your meter. If it does not, check your leads for damage and make sure they're plugged into the right spots on your meter. Now, touch one lead to each side of the component or isolated portion of the circuit you are testing. Wait for the display to stabilize and record that number. This is the resistance. Resistance will always be shown in ohms. Resistance across an open switch will always be OL. By the way, notice the circuit breakers between L and neutral and the rest of the circuit are open. That's making sure there's no power on this circuit. But a resistance across an open switch will always be OL. Resistance across a closed switch should be 0. If you get OL, that means the switch is open internally. Nothing you can do. Replace the switch. So in this case, I'm reading OL. Okay, but it should be 0. Replace the switching device. Resistance across a good load is some number. It's all dependent on the load. Okay, it's some number. Resistance across an open load is going to be OL or infinite. OL just means infinite. To measure current, the first step is to determine which method you want to use. It is possible for the clamp to use the clamp for higher voltages and currents. It is possible to put the meter in line for lower voltages and currents. Be very careful on the second one that you do not overwhelm the meter. Always try with the clamp first. To measure current with the clamp on meter, make sure the system is running. Clamp the meter around a single wire. Don't do line and line 2 or line and line 1 together. They'll cancel each other out. Wait for the numbers to stabilize. This is your amperage reading. If the current is too low, consider putting the meter in line. If it is not possible, wrap the wire around the clamp 5 to 10 times, take your reading, and divide the number you get by the number of times the wire is wrapped around the clamp. For example, if the wire is wrapped 10 times around the clamp and you read 2 amps, then 2 divided by 10 is 0.2. To measure current in line, put your meter in series with the circuit. Okay, in other words, you have to make a break in the circuit, put 1 meter lead on one side and 1 meter lead on the other side. Again, be very careful on amperage on this one because you can damage your meter. Make sure the power to the circuit is turned off. Check with your voltmeter to verify this is the case. Disconnect a wire directly before the component you're concerned about and put the meter in series or in line with that component to complete the circuit. Make sure the meter is set to amps and the leads are plugged in to the correct spots. Turn the breaker back on and allow this display to stabilize on the meter. This is your amperage reading. Again, word of warning, every meter will not do this. Make sure you've read the manual and make sure your meter can do it. Make sure that you know the levels of voltage and current that your meter is rated for. Never exceed this voltage or current. If you suspect it's close, should be using the clamp-on method instead. Now, you'll often hear things referred to as a hop-scotch method, okay, of checking for breaks and troubleshooting systems. Unfortunately, most of the time you'll not just have one switch controlling one load. Most circuits in the HVAC industry will have more than one control device. You must have a reliable and organized method to find problems in the circuit. This is why most good technicians start off any diagnostics by using the hop-scotch method to trace circuits. The procedures for this is extremely simple. First, make sure your meter is set on volts and make sure the leads are correctly plugged into the appropriate places on the meter. Next, check voltage across the 2 endpoints of a circuit, line and neutral or line and line. Put 1 lead on the start point of the circuit, or in our case L1. Keep that lead there. Use the second lead to go from point to point in the circuit before and after each switching device and load and check for opens until you find the problem. So we're going to start with L1 and N. We want to make sure we have power to the circuit. Now I'm going to leave 1 lead, clamp it on to L1 and to the line side of switch 1. So we have 0, so the wire from L1 to switch 1 is good. Now, voltage across L1 and the load side of S1 is 120 volts, means switch 1 is open. Remember, the voltage across an open switch is always source. You can verify this problem now by starting from neutral. Voltage from neutral to neutral side of B1 is 0. The wire is good. Voltage from neutral to line side of B1 is also 0. Voltage remain no problem from that point. Voltage remains 0. Voltage from neutral to line side of switch 1 is 120. Problem found. Switch 1 is open. Remember, voltage across an open switch is always 0. And just a note here why we go through this. When you're in the field, you cannot see inside these switching devices. You have to be able to do it from your meter alone. A couple rules. Voltage across an open switch is always source. Voltage across a closed switch is 0. Voltage across an energized load is some number. Voltage across an energized non-working load will always be source.